Welcome to the last day of this summer school. So this is, you already know Inanç Hoca, so I will just leave the floor to him for his second lecture. So Inanç Hocam, the floor is yours. Enjoy, guys.
Great, I will.
No, yeah, I mean, enjoy was to the audience.
Okay, well, I will enjoy as well. So now so let's start from yesterday's. I mean, a couple of things from yesterday. First of all, so the adiabatic approximation, remember, requires you to have some sort of external parameters which you control time dependently adiabatically. So here, and then there's a concept called Berry phase and Berry curvature coming from that. Now we use that to describe our momentum space of band insulators, basically. Right, so that's the trick we are doing. So here there is no notion of adiabaticity, right? So we don't really need adiabaticity. So you can be actually for instance your chemical potential might be somewhere inside, right? You might even have a metal. You don't have to be in the band level. So you could actually have some of these effects laying there with you. So in fact, so maybe that is an interesting thing to mention, is that so if you sorry, just dropped my phone. So if you actually had this Berry curvature in a band, you don't even need. Let's see. Let me just move this. I will come back to that in a second. If you had a Berry curvature, right? So remember, we are denoting it by this thing called omega, right? So in 3D, in a momentum in the momentum space, you might even actually be in a metallic thing. As long as you don't leave the band, you would actually feel the effects of this Berry curvature. And one of these effects is that it's actually, if you have it, if it is non-zero, and if your electron is moving around, you might have remembered from your condensed matter courses. Remember, you actually Ashcroft or Merman. I learned condensed matter from Ashcroft or Merman. So it basically it will tell you that it talks about basically a kind of a 19th century or 20th century Newton that talks about, basically looks at the dynamics of particles who are living in crystals, right? So you have this band structure. So basically you have the same thing as in Newtonian physics. So once you quantize, you got the band structure and so on. You try to go back, you get some sort of semi-classic description. So how does the particles, let's say if you have a wave packet, how does that wave packet move? And if you actually did that in the presence of Berry curvature, something that you actually is missing from most books is that this one, right? So typically you have the equations of motion written like this, right? So you have the r dot, right? That's the velocity, right? This is equal to del epsilon over del k, right? Here I'm taking h bar to 0. Sorry, h bar to 1. H bar to 0 would be really cool. So I'm using Unispin h bar as well. So that you have this as epsilon over del k. This is our usual Hamilton's equations of motion. And then you would have your k dot, right? So this would be minus del v over del r, right? That's the potential, right? And this is the nabla, right? Maybe you want to see it as like that, minus grad v. That's what it is. That's the notation. So now, if you have a magnetic field, you also have minus E dot R cross B, right? So this is the magnetic field, so you have the electric field in the first term, you have the magnetic field in the second term. They change your momentum, and your velocity changes according to where you are in momentum space, accordingly to the gradients of the energy, right? So this is the usual thing that we know. Now, if you have Berry curvature, right, and you do most of the time, you actually have a term like this, K dot cross omega. So you see that it turns, so then you see that actually it looks like the Berry curvature looks like as if you have you have the magnetic field in the real space that gives you a kind of a Lorentz force on the momentum. And then you actually have, looking at this, you actually have a Berry curvature in the momentum space that gives you an effective magnetic field that tries to turn your velocity, right? So it adds to your velocity. So then you have a very symmetrical things, right? So these are the, the classical or semi-classical equations. So here, for instance, when you're describing even quantum mechanics of a particle like this, you don't need to have any adiabaticity, except that there's some little bit of notion left, if you want, is that you want to be stuck to that band. Okay, so this is, for instance, like this, something like this we also already assume, right? For us, whenever we are doing this electronic things, we say that we are stuck to the electronic band. We don't do anything with the positrons, although they're there officially. They might actually mix into our quantum dynamics. We say that, you know, our energy and so on is so low that we don't excite those electron hole pairs along the way, so you know that they don't affect our dynamics. This is similar approximation. Now this is case number one. So situation number two, so this is what I was trying to draw yesterday. Remember, I was talking about symmetries. So these are basically anti-unitary symmetries. Remember, there is the time reversal symmetry. So you basically, in both cases, you take the complex conjugate of your Hamiltonian, right? Not the Hermitian conjugate, complex conjugate. Remember, Hamiltonian is Hermitian. So Hermitian conjugate will always be equal to the Hamiltonian, right? So there's nothing there. So it's critical you take the complex conjugate. For instance, if you have, for instance, an operator like the momentum, right? The momentum operator is minus I h bar del over del, it is px, then this is del over del x. If you take the complex conjugate of that operator, right, px star is equal to minus px, right, because it's complex. I in front of it would give you 9 minus. On the other hand, x would be a real operator. So remember, there are like some subtleties. If you're interested, I would suggest that you read Sakurai has a very nice section on this, explaining the anti-unitary operators in quantum mechanics. What Sakurai does not have is that you also have another one, right? So you take once you take the complex conjugate, you make a unitary rotation, right? So you can, the question is, whenever you take a unitary rotation to the Hamiltonian itself, that means that you have some sort of real condition in some basis. In some basis, your Hamiltonian would be a real operator. Okay, so that's what it means. There's also a particle hole or the charge conjugation part that actually does it. You take the complex conjugate, and then you can actually use a unitary transformation or a change of basis to show that your Hamiltonian is actually, that complex conjugate gives you the minus Hamiltonian. So that gives you some sort of symmetry in the positive energy and negative energy excitations. And then looking at that, you would actually have the symmetry. So these are and then remember that whether or not you have these, you have the option that they would either square to 1 or they would square to minus 1. You would have you have 9 options, and then you have the 10th option, which is right here. Let me just use a different color here, right here. Right, so that's the case when, even though you don't have time reversal and charge conjugation, their product remains to be you still have this sublattice symmetry. You have the product would remain to be a good symmetry. So now, what you see here is the dimension, right? So you say that you first find out what's your symmetries of your Hamiltonian, and then try to figure out what sort of topological state you might actually have. You would look into this, based in this table, right? So these are some of you might know this. For instance, there is A, right? So you can see, for instance, in 2 dimensions, A can have a topological index Z, right? So all the insulators, when you have no time reversal symmetry, no charge conjugation symmetry, no, based chiral symmetry, whatever, nothing, you have no symmetries left. Nevertheless, in 2 dimensions, you can have a topological state characterized by Z. We actually all know this state, right? So you imagine you have a particle, you want to break time reversal symmetry, so you apply a lot of magnetic field, right? If you have magnetic field, ultimately you go into some sort of insulator state, but then that insulator is different than our vacuum, and if you have a boundary of that, basically of that insulator with our usual vacuum, you see that there are actually edge states popping up. Those edge states and the state here we know is the quantum Hall state. Right, and then the quantum Hall numbers, you can have any number of edge state, including 0. So this would be your topological index. Right. Similarly, for instance, another example is, for instance, you can see that in D1 and D3, for instance, have these are basically that I will actually especially going to talk about this D and BD1. Remember, we talked about BD1 in the beginning, hiding it. You could, when we off-diagonalize everything, you see that, for instance, you can have an index, but you can actually have any number of 0 modes on one sector, right? So that's why you get this index Z. you know, in D, this is what you want to do, is that you have basically become the zero modes, right? Those zero modes all hybridize, except if you have an odd number of zero modes, that even though they all hybridize, there would have to be one left, because you have to have the symmetry of energy minus energy. And if you odd number, that one of them has to be stuck there in the middle, right? So that's why this is where you want to be whenever you're doing topological quantum computation, and that's the state D. And to get that state, you have to break time-Russell symmetry, but the charge conjugation symmetry would remain intact, right? And that is actually good, because what we're going to do is that we're going to use superconductors. Good. So now, if there are any questions, if there are no more questions, so this is from yesterday's thing, so we can continue on. How am I doing on time? Let's see. So now, our main idea is that, remember, we had the zero modes, we had the Hamiltonian. So this is the kind of the most, you know, maybe we have to jump up and down a little bit around, because what we have to, for what we're going to need, we need to have some sort of a slightly different language than our usual quantum mechanics, you know, first quantization language, right? We do have to do second quantization, but you have been seeing in you know, Özgür Hoca's and Ceyhun Hoca's and so on, and especially Oğuz Hoca's things that you were talking about. You were looking at basically photons. Özgür Hoca is asking a question. Yes.
Before you proceed, so when you said this topological quantum computation, topological insulators, the dimensionality is also preferred.
I'm sorry, I couldn't. Could you repeat?
So when you said that topological quantum computation prefers this D-type topological insulators, and is there also some preferred dimensionality, like 1, 2, or 8 is better, or?
Yeah, that's the thing, right? So I haven't talked about dimensionality. So if one thing to be said about the dimensionality is that you see that there's some sort of repetitive structure. That's actually it's an old thing called Bott periodicity. Mm-hmm. So these are basically, you know, you can actually, these are very nice results from, you know, basically math. But here, usually you talk about low dimensions, you know, 1 and 2 dimensions and so on. So the main idea is that you want one dimension in this. I'll come back to this in a second.
Okay,
so we can discuss that later.
Thank you.
Okay, so now we have to do this. So you have seen some creation annihilation operators, right? So you have this A's and A daggers. Now we have to talk about the fermionic versions of that, right? So that's the key thing. And then we want to isolate one of those zero modes in the superconducting context. And then I would like to try to see, you know, what you can do with them. So now typically. Okay, so that's blue, that's not really good. So now we have topological superconductors, right? So we start writing a Hamiltonian. So I'm going to just write it in this way. So you have typically an integral or whatever sum over all quantum numbers. And typically what you have is that you have a Hamiltonian in the center. I'm going to assume that I have a single spin species. Okay, so there's only, let's say, upspin electrons. Okay, so now the upspin electrons would have a Hamiltonian like this, right? So you have the H. This is a single particle operator, right? Minus your chemical potential, H minus mu. So now you want to say, of course, that this multiplies some sort of creation or annihilation operator H psi, and then creation operator psi dagger. So now what I want to do is that I want to write a psi dagger here. So this is how you typically write a mean field superconducting Hamiltonian. So instead of see how you can do this, I'm going to first write it down and then try to explain what happens. Now my H here is p squared over 2m, right? So that's just my usual good old one-dimensional number. Right now here as a whole, right, you have basically, you can, instead of looking at stuff as you have this p squared over 2m and then you start filling up the electrons, you can actually have an equivalent way of, you might have seen this in condensed matter or many body courses, you know, you can actually look at it all from the point of view of the holes. You can say that you know, you fill up electrons up to here. You say, no, no, no, I fill up all the holes up to from top to this point, and only the hole states that are unoccupied are down there, and so on. And the thing is that it will be completely equivalent. So that you do here, right? So the fun thing, and that's minus h minus mu. Now what superconduct, so this is just so far, if I didn't do anything, I'm just basically playing games, right? I just said, oh, I have the electron picture that the electrons are dynamical, and then I have the whole pictures that are the whole can do the whole. They on their own, they're the same and they will equivalent to each other. So now what basically what superconductor tells us is that actually these two degrees of freedom are coupled, right? So that you don't not like it's you see that they're actually so one thing is that they're obsolete degrees of freedom, right? You actually describe the same thing in two ways. So what does it mean that they're coupled? So it means that you have actually an operator here and delta, right? So now this is, I'm going to put a hat on top of it. So now this, what that means is that you actually, this thing is also obsolete, right? So the equivalent, the outcome of this is that you will see that you only need to consider, if you're looking at excitations, only positive energy states, right? So now there is a very important thing here. So you can see that if you look at what delta does, right, it will actually multiply, right? So for instance, you would have terms like psi dagger of x, which creates electron at point x, psi dagger at point x, and the delta, right? So if you had delta is a constant, but this cannot be because that means that you remember this is only a single spin. You cannot put two spin electrons at the same time, right? So remember, so this term is not possible. So the next thing that you can do is that you can do the whatever is nearby. So that would be psi dagger, right? Basically some sort of I del x, right, times, let's say, psi dagger. Right, so this would be possible. Okay. So now if you do this, so the next thing what you do is that, so now you have written your Hamiltonian. So then you call this part the single particle part. And this is your full real, if you want the big, nice Hamiltonian, right? Remember, and the main idea here is that these are fermionic states. That means that they basically, the only thing that you do is they're just like your A's and A daggers. They create excitations and things, and a psi of x would, for instance, annihilate a part electron at point x, and they have to anti-commute, right? So you have this condition psi of x, psi dagger of two daggers. If you have an anti-commutator, this would be 0. That ensures that you have fermionic statistics, right? If you have psi and psi, it also be 0. And then you have psi dagger psi. This would give you a delta function of x minus x squared. Right, so at different points, they anti-commute, but then exactly you have a condition that at the same point, they give you this condition, okay? So this is a key thing because as long as you have these operators, you're fine. So now, typically what you do is, and I know I'm kind of going in a crash course, but just think of it as, if you have any questions, we can of course discuss that later. But the main idea is that I want you to see where that zero mode comes into a context like this, right? So the main idea is the following, right? So you say that, hey, I have this single particle operator. I want to write this basically some chi n, right? And then I want to solve single particle picture operation. This is what I have been doing, right? So you solve single particle picture. Now with that, I know that from my old things, this chi-ans form a complete set, right? And then you expand your field operators, psi and psi dagger, in that basis. Right? So you have the gamma n times basically chi-n. Let me just put under something to show that this actually is a spinner. Right, okay. So now, you just do this, and then if you plug this in to your Hamiltonian, right? So that's the key thing. Right, so you have your Hamiltonian. Let me just copy and paste it. This is your thing. Copy. Paste. Now the important thing here, I'm just going to be basically, I know I'm glossing over the calculation here. So you want to put this sum instead of that. You want to put in sum, oops, over n, your gamma n times chi n, okay? And now this operator acting on that chi n would give you some epsilon n, okay? And then you would have, basically, you would have to do the same thing here and so on, okay? So now this will give you, because you have a complete set, right? So remember this chi n's form a complete set means that chi n dagger chi n integrated over is actually a delta function n, right? So using that, you can show that your Hamiltonian is something like epsilon n gamma n dagger gamma n, okay? So now you have this, you did something like this, well, that's really fun, but then remember we have this, what about this particle Hall symmetry? You would find out that the particle Hall symmetry comes into play like this. If you have this gamma n, right, remember this is actually shorthand for gamma at epsilon n, right? You would remember, because of this structure we actually had for every epsilon n, and this Hamiltonian has that feature as well, you have a minus epsilon n solution. So you have a solution, this is a solution for epsilon n, you also have a minus epsilon n solution, right? So this is your gamma of minus epsilon n. You would find out that this is actually equal to gamma dagger of epsilon n. Okay. So you have this condition, right? So this is kind of a important condition, let's say. Just put it inside a box. Right, so this is what we mean by when we mean a Majorana fermion. Okay. So there's a key thing, so which means that basically any quasi-particle inside a superconductor is a Majorana fermion. Okay, so sometimes we call them both, condensed matter people call them Majorana quasi-particles. So now, and the more important thing is that if you look at these, the commutator relations of this gamma n's, you would find out that they satisfy the same commutation relations as your psi, right? If they anti-commute, then if you have, you have them exchanged and so on and so forth, okay? As long as you look at only positive energies. And there's this kind of this peg doubling there. Now, the key thing is that, and so that therein comes a lot of people making mistakes. Like, I mean, it's a nomenclature mistakes, but then, some people who are in the field, they think about, they know this, but then, they use sloppy language. And then the people who are a little slightly out of the field, like, I mean, Barry Sanders, like just a couple of days ago, talking about this in a mistaken language, it's not Majorana fermions are fermions. So you cannot do topological quantum computing with them. They're fermions. Okay, so that's the key thing. And they've always been around. No one is looking for them. Anytime you're looking for any Andrew bound state, whatnot, laying around, you see them. We have zillions of signatures of them, and so on. There's this Caroline metric indigency, all sort of states that actually are, have this Majorana character. So now the key thing comes in whenever we're looking. Remember, these solutions have the zero mode, okay? And therein comes the key thing. So now for if we have a epsilon equals to 0 solution, okay? Now this condition of being a Majorana, right, it gives us something very special, right? So gamma dagger of 0, right, is equal to gamma of minus 0, right? Minus 0 is 0, so it is basically tells you that these operators, right, these particular operators are Hermish, okay? So now this is the key thing. That's then called a Majorana zero mode. And if you have them isolated, and this is the elusive particle, right? So if now we're going to see that it actually has statistics which are not fermionic, right? So they're actually non-abelian anyons. Okay. So that is the key thing, right? So these zero modes are the ones that we want to look for. These zero ones are the ones that we want to achieve, not Majorana fermions. Okay, Majorana fermions are there, but whenever you have quasi-particles in a superconductor settings, that's the Majorana fermion. Okay, so now we want to have these zero modes, and remember the zero modes are actually related to this topological index, and whenever you have these, you call that a topological superconductor. Okay, so whenever you have exactly the same thing applies. For instance, if you had a wire, we can discuss if you have time how to make these and what are the things. If it is a topological superconducting wire that goes into some trivial, vacuum or some trivial insulator, then what you see is that you see a Majorana zero mode here localized. Now, of course, you can see that that also key is another key. You cannot have a single one of these because they're not. You see that they're not fermions. We started out from fermions. So whenever this happens, whenever you have the zero mode, they cannot come in alone, right? They have to come in pairs, and this is the other one over there. Right. So these are now the gamma zero, if you want gamma of zero, right? This is another gamma of zero here. Let's just call this A, and then let's call this B. Okay. So now the key thing is that you see whenever this happens, right, you can actually form a fermion, right, called basically a fermion operator, basically by combining these guys. You have the gamma A, right, plus I gamma B, and then, well, we divide it by 1/2, right? You call this a fermionic operator C. Okay, C dagger. And then you can, of course, have the same thing, gamma A minus I gamma B, 1/2 would be C. And then you can immediately show that the C dagger satisfies fermionic commutation relations. Now you say, okay, so this is a very good thing. There's something in the chat, maybe I'm missing out. Anything? Can the zero modes come from the violation of chiral symmetry, existence of chiral anomaly? Can this produce a chiral current in the system, produce a chiral magnetic effect? Okay, so we have to come back to this as well, because there's a kind of a lot of chiral nomenclature here. I'll come back to that, but let me just say that chiral anomaly happens in 3+1 dimensions. So it is a thing of, while superconductors, we actually have a work on that to show that you can actually have that. The chiral magnetic effect, then we were looking, when you're looking at some sort of wild semi-metal or wild superconductor in 3 dimensions and 1 time dimension, right? So here what we're looking at is something like a very, very, very low dimensions, basically talking about 0-dimensional stuff that are bound to something, right? The edges of a wire, right? We also can see that these can be, if you have a vortex, they would also be coupled to that, and so on. Okay, so now, so the key thing here is that, and then I will move on. Let me see how much time I'm having. The key thing is that basically, if you have these operators, you see that this is like another, again, a fermion operator, and you can say that then I can write any fermion operator like this, and it is true, right? So that is the key thing, right? You can actually write any fermions like that, but here, gamma A and gamma B are localized at different points in space. If you take any electron, you can write this operator as, again, in its own gamma A and gamma B, right? But that will be localized in the same point where the electron is. Here, the key thing is that they're separated. So that's called electron fractionalization, right? So you actually fractionalize an electron, right? So whenever you're looking at locally, there is no electron there. There is no electron here either, but together they form one fermion, which is delocalized at the 2 ends of the wire, okay? So you basically are splitting electrons, yeah? Or you can say that you're splitting the real part of the electron from the imaginary part of the electron. But, so that's why we have math. So it's clear what I mean. So now, I would like to talk about why these, so far so good, right? So this is nothing, since you can write these operators from all the electrons, what should be the hard part? right? So this is now we're going to show that these operators are actually non-abelian anyons, and then you can use them to do some, basic computation, or you can have them do some compute operations. But the key thing here is it's already visible there. You see that you have a state like this. Remember from that, so your ground state of your superconductor, let's say you call that 0. If you write a C dagger, you actually can have another state, let's say 1. So you have a fermionic state delocalized at the ends of the wire. When that state is empty, right? So you call that 0. When that state is full, you call that 1. So now this is a very special superconductor. It means that basically its ground state, remember that in terms of its fermion, typical superconductors we know have ground states that have even number of fermions. It's the Cooper pairs, right? You have this, all electrons are paired, and then they condense, and then nothing, all the single electron excitations have to pay a certain excitation. This is our conventional picture. Now, what happens here is that you basically have a topological superconductor. That's true, there's still that gap, but you actually also have these little mid-gap states that are exactly telling you that you actually have an even number of electron ground state and an odd number of electron ground state. Okay? And they have the same energy. Okay? So now, but there's a key thing. So one obvious thing is that, hey, look, I have 0 and 1, I have a qubit. That is not correct. We have not yet a qubit. And the reason is the following: you cannot superpose, right, particles of different fermion numbers, fermion parities. Right? So this is a very key thing that you cannot. Özgür Hocam, maybe this is kind of a similar thing that that basically not entangling with the vacuum, but it is. So here, the important thing here is that you basically you have to those fermion numbers are inherently conserved, and the fermion parity is in a superconductor. You remember the fermion number, the charge and so on are not conserved because you can actually exchange charge with the condensate, with the bosons, but still your fermion parity is conserved, right? So that's the key thing, and the reason is that you basically have a Cooper pair, right? So if you actually you can have a Cooper pair and a hole, right? You can go between this and an electron, right? So basically what you do is that the fermion number here, or the fermion parity here and the fermion parity there, have to be equal. Okay, so these two states, 0 and the 1 state, have different fermion parity. Therefore, you cannot, put them in a superposition and whatnot. Okay, having said that, now let's go back and then imagine now how do we actually do this computation, right? So the main idea is that, so now you actually have basically, typically people have this wire networks and things like that and so on. We'll come back to how you can actually braid them and so on. So imagine you have many of them. Right, so you have gamma 1, gamma 2, and so on. Right, here is the gamma 2n, and then you have gamma 2n plus 1, gamma 2n minus 1, and so on. Okay, that's many of them along the way. All right, so now the important thing is that, remember, I can, if I want to describe the state of the system, I always combine them into the Cn operators. Right, so I talk about I make up a fermion. It's just the basis that I'm used to, so that I would like to use it in that basis. And of course, remember that basis ultimately, whenever you're doing any experiments, is the basis you would use, because those are the bases that you can couple to. In that basis, you can count fermion number and so on. Okay, so now you do a Cn dagger, right, as gamma basically 2n minus 1 plus I gamma 2n divided by 2, and then you have Cn is the complex conjugate 2n minus 1 minus I gamma 2n divided by 2. Okay, so now you have these two states, right? And then your basis state is, again, would be states which are formed by these fermions. So Cn dagger is a set of fermions, right? Remember, so they might be occupied and unoccupied, right? So whenever you're having a state, let's say you're talking about 0, 0, 0, whatever is 0, 0, 0, 0 state, You act on it with a Cn dagger that gives you a state which is 0, whatever, and only this 1 at the end point, and then 0, 0, 0, and so on. Okay, so you can, and the key thing here is that because these are Majoranas, they're separated, they all have the same energy. So you have a massive degeneracy of your ground state. Okay, so this is kind of the platform you want to achieve. Okay, so suppose you achieve this, how do I actually show that they are non-abelian? So let's just go there. So now the important thing here is that, so remember, there is an amazing, well, there are actually a couple of ways of actually doing this. So, so let's just do the following. So imagine now, right, I do something, right, such that they would actually, my, if, right, so that's a big if. If these fermions had been at the same point, right, you could actually give them phases, okay? Right, that's kind of a gauge freedom, and basically those are the phases that actually we don't like, right? Because that phase would mean basically that you actually are, randomizing your quantum state, and then if you, that phase that is uncontrolled will actually wash out all your quantum superposition, all the interference effects and entanglement and so on. Okay, this is not good for quantum. Now let's just write down this gamma business like that, right? So I have gamma 2n minus 1, right, is equal to gamma basically, sorry, Cn dagger plus Cn, right, that is it. And then I have gamma 2n, right, so this is basically Cn dagger minus Cn over I, okay? So now I ask myself, like, let's just say that, and that's the key thing, right? So now if I make a phase on this fermion somehow, right, then this would cause a transformation, right? This will become, I have Cn dagger, right? And then I would have Cn dagger times, let's say, e to the I theta, right? That's my phase. And then, but then the Cn would pick up e to the minus I theta. Right, so the same thing here, right? So let me just go on a little bit further. So this would be my new fermion. But then I can actually write this as cosine theta times Cn dagger plus Cn plus basically I times sine theta times Cn dagger minus Cn. Okay. So now you see that this is a cool thing, because now you see that this was my original gamma, right? This is my gamma 2n minus 1, and this one is basically I times gamma 2n. Okay. So now if you make that phase transformation, right, on your fermion, what it does on the gammas is something very non-trivial. So it actually have your gamma 2n goes into gamma 2n cos theta minus gamma 2n minus 1 times sine theta, and then gamma 2n minus 1 I haven't showed you, but you can guess this goes into gamma 2n sine theta plus gamma 2n minus 1 cos theta. Right, so it makes a rotation. So now if your electron and your gamma n and gamma n plus 1 are on the same point, this rotation is non-trivial. This happens all the time. But if they're separate, okay, so whenever you do this, you actually are effectively like putting in very non-local operation. Remember, sub one is here, the other one is there. So that's why the environment is unable to come up with an operator that does this. Okay, so that's key number one to topological quantum computation, because the environment cannot do this. It cannot actually operate on your quantum state of your system. So now what remains is that we want to show that this actually does the trick for our braiding operations. So now let's just talk about the braiding operations. The braiding operations, actually, you see that you have a situation, right? So you want to, let's say, exchange your gamma 2n to gamma 2n minus 1. Right, so we're going to start with that, and then we're going to see that actually this one will give us something trivial. but we will see that as you go, you get something non-trivial. Now, suppose I want to exchange these guys. Right, so the operator that does this, right, have to do some operation like this when theta is equal to, remember, whenever I do, so I want that theta is equal to pi over 2, okay? When theta is pi over 2, I have an operation gamma 2n goes into minus gamma 2n minus 1. I have gamma 2n minus 1 goes into gamma 2n. So now this operation, so and that's the key thing, because I haven't, so I can describe it as a phase and but that is not good because I want to have a real operator that acts on it, right? So then I can actually generalize to all the stuff. And it turns out the operation that does this, right, is the unitary operation, right? And this is if you want the braiding of basically 2n with 2n minus 1, right? So this is equal to e to the basically pi over 4 times gamma 2n minus 1. Remember, it's a key thing, right? This gamma, their product is anti-unitary, so that's why this is a phase. So the important thing is that you can actually, as homework, show that this produces the transformation. Let's call it star with theta is equal to pi over 2. Okay. So now, because I'm running out of time, I would like to move on, and I would like to show you that this is the moment that I have this operator, I actually can generalize it to any of the two by exchanging those two particles. This is the operation that changes one particle to another particle, right? So the most general thing, u of gamma n and gamma m, right? This is equal to e to the pi over 4 times gamma n gamma m, okay? Now, this is the key thing, right? So I don't know how am I doing on time, so I can show you how this goes, at least.
Hocam pardon, yaklaşık 5 dakika falan kaldı.
Tamam. All right, so, okay. So now the important thing here is that if you see the state, so the moment I have this, right, so the only thing that I want to show, actually I will give you also a hint for the homework, so that's actually pretty good. So also a hint for the homework, right? So remember this gamma n, if you look at it, and gamma m, right? They anti-commute unless they are basically the same operator. Then they don't commute. So which means that basically gamma square is always 1. Right? It's an identity. Now this is an important thing. You can actually get them out from these relations if you want, if you find them, you know, if you find them non-trivial. Now looking at that relation, you have you can show the following. So you have gamma n and gamma m. Remember the anti-commute. If you square this, right, you have gamma n, gamma m, gamma n, gamma m. Right, n is not equal to m. Right, so then I can actually change this one to that one. That gives me a minus sign. Then you have gamma n square, gamma m square, which is 1. So this is equal to minus 1. Okay, so this operator, gamma n, gamma m operator, when they're not the same, right, it squares to minus 1, you know, all these operators square to 1. So this actually looks very much like a Pauli sigma matrix, right? If you do this expansion, then remember how you show to be able to show that, you know, e to the I, to show the spin rotations, you always have to expand the exponential. You do the same thing, right? So to expand the exponential, you see that every time that you have an even number of gamma n to the power even number, you would get minus 1 to n. And then whenever you go to the odd number, you have something like gamma n m times something even number. And that gives you a generic thing, right? This U, if you have a, so let's just say that's exponential times basically beta times gamma n, you can actually expand it just like your Pauli business. That would be basically a cosine beta plus gamma n times sine beta, okay? So now you have this operator, you can actually go play around with stuff, you know, like that's the key thing. Now, remember for pi over 4, right? If this is for beta is equal to pi over 4, right? This would be basically the following, right? So this would be cosine beta would be 1 over square root of 2 plus gamma n square root. Right? So this would be basically 1 plus gamma n divided by square root of 2. That would be the operator that exchanges gamma n and gamma n. So now let's just to demonstrate your thing, let me just do this real quickly. So now let's just say that I have actually 4 of them. 1, 2, 3, and 4. Remember that these 2 would make your operator C1, and these 2 would make your fermion C2, right? And then correspondingly, you have the states like you have the 0 fermion state, you have the state with C1 dagger 0, 0, right, which is basically 1, 0. And then correspondingly, you have the 0, 1 state, and then you have the 0, 1, 1 state, right, which is basically C1 dagger, C2 dagger on 0, 0. Okay, so this would be then the degeneracy of 4 in your state. Now, the key thing is that now suppose I make the transformation 1, 2, right? So the transformation, I want to exchange 1 and 2. The operator does that. U gamma 1, gamma 2, right, is equal to 1 over square root of 2, 1 plus gamma 1, gamma 2, okay? So now this is, you know, you can actually show that this is a phase, which is not surprising because that's just how we came back from there, right? So that if you have an operator, this actually gives you a phase of, you know, basically, remember this is a phase of pi over 2, right? So it's just multiplied by I and so on. So now this is something which is trivial. So if you get this U1, 2 acting on the state 0, 0, you actually get a phase which I will ask you to calculate on that 0, 0. Nothing really changes. Now let's imagine we do the following, U2, 3. Now this is something non-trivial because this you cannot ever do this unless you have stuff that is separated, right? You take the, let's say, the real part of this electron and the imaginary part of this electron, and you exchange that, right? So now comes, and then at any point in this exchange, you can actually move them apart from each other, so they will never touch, okay? So now let's see what that operation does, right? So this operation is 1 over square root of 2, identity operation times gamma 2 times gamma 3, right? So now how do I write gamma 2 and gamma 3? Remember my definition, right? I want to write it in terms of the fermion operators in this form, right? Let me just copy that there. Copy. Paste. Now this is let me just put it in a box that I'm going to use. Now if I want to write it in this form, right, so my U2, 3 operator, 1 over square root of 2, 1 plus gamma 2 is this operator, right? Cn, or not in this case, of course, n is equal to 1, right? This would be C1 dagger minus C1 divided by I. Gamma 3, on the other hand, right, it's an odd operator. So this for n is equal to, again, n is equal to 2, right? That would be basically C2 dagger plus C2. And this would be the operator. Now let's see if I act this on the state 0, 0. Right, so the operator like this, 1 over square root of 2, identity plus C dagger 1 minus C1 over I times C2 dagger plus C2, acting on 0, 0. Now, the important thing is that you probably need to see this. This is an annihilation operator, on a ground state, so they would be killed, right? So they will annihilate the state. So I basically have two options. So I would have 1 over square root of 2 of the state 0, 0, that's coming from the identity. And these are the states that are basically like you basically have the thing which is plus times 1, 1. So there's something in the chat. Okay, so that's already, I'm afraid that might probably even finished. So now, but I'm at a point that I can now talk to you about. This is like a typical situation of bul parayı al karayı, right? It's the thing of cups. So what you do is that you start out with a state, right? So you have these fermions here, right? So now you basically germinate them from vacuum, right? So you have the states 0. You start out with a state of even fermion parity. You have no extra fermions around. You start these two Majorana fermions, gamma 1 and gamma 2. Together they form a fermionic state, delocalized, and they have no fermion on that state. You have gamma 3 and gamma 4, also a state like that. There's another fermion there. So this is C1, this is C2, and both states are fermionic states are empty. Now you make this operation, you take, gamma 2 and move that here, gamma 3, and you move that there, right? You move that operation at any point. Now your state of this being from 0, 0 goes into a superposition of 0, 0 plus 1, 1. So it can be that I made a sign convention somewhere that you might have a -1 corresponding to this as well. It really doesn't matter because it depends on which direction you actually move them. So now, I mean, that's an amazing thing. Now you started out as no fermions from anywhere. You just move this around, and all of a sudden you have a superposition of now fermion and no fermion. So now, if you want to measure this, for instance, you can bring them again back together, right? Together they form, they were delocalized fermion. When they're on top of each other, they become something measurable, right? You can measure the charge and so on, that sort of thing. You make a charge measurement, and you find out that not all the time you see no fermion. You basically started having a situation where you have fermion, and then you actually started making some sort of a very strange looking state. So now the key thing here is that this is basically is a gate operation, and this is a gate operation that it is in a sense topologically protected, right? So the key thing here is that as long as your gap is large enough and your system, you can operate the system basically by moving them around, you can generate this operation, right? This is, if you want, is a qubit operation. This 4 Majoranas form 1 qubit because you have a fermion parity. So this is the operation that you can do is only between 0, 0 and 1, 1. Plus you can actually have these phase change operations on 0, 0 and 1, 1. Right? Those are the 4 things that you can do here. Now, but if you have 8, you have 2 qubits, you can actually start moving various gammas from one to the other, and that will actually start entangling them. You see that what's coming out is extremely complicated stuff. So that's what they call braiding, right? It's like a braiding saç örgüsü, right? You have these electrons, basically, you have those Majorana fermions coming out up there, and then you basically are moving them around in various, ways. This can maybe do nothing, and then you can get this one over this can go out, and then you can have this one now coming that way, this can go here, and so on, like, so you can actually make this move as basically time goes by, right? So now you can actually start from a quantum state here, and then you can of course have many of these, and you can see that by making those operations, you can actually end up with a state that you desire, right? And remember the whole point of quantum computation is that you want to be able to control operations on your particle, on your quantum state. Here, the key thing is that there is a big problem. There's a kind of, if you want, is a contradiction in quantum, computation. You want to be able to couple well to the system enough that you want to operate on it, but you don't want the system to couple to the environment so that the environment doesn't operate. Here, this way, you can have achieved both worlds. You basically can operate on it in a very controlled, deterministic manner, by changing the position of those things, by using actually gates and so on. And that was the key idea. So if you ask me later on, I can tell you about what's the recent developments and this retraction business and so on. So now, and then you can actually, by making these operations, while you're doing that, at any point, your state is protected. So now there's this one key question. So, okay, so this is now your final homework. So how do you actually transform, and this is a key thing, just if you suppose you want to transform 1 and 3, they're not right next to each other, right? So how do you do it? You can actually show that this is equal to U dagger 1, 2, U 2, 3 dagger, and U 1, 2. By making these operations in the sense show, this is show this. By making only the nearby operations, you can actually make any operation in global operations and everywhere. So that's the key thing. So now there is one key question, is that can you do universal quantum computation with only these operations? The answer is no, there's one operation missing. Okay, so that's the, of course, you can of course do this operation whenever you bring those qubits together, and there are proposals that people want to do this in a very, in a protected manner, but yet there is no topologically protected way of getting this final missing piece operation. Okay, so that's the and that's the kind of the golden, let's say, holy grail that we want to find, right? So this is the key thing. So if you actually have it, you answer the question that definitely guys at Microsoft wants to be answered. Okay, so now I'm going to stop here. If they have any questions, I can answer them.
Okay, thanks a lot, İnanç Hocam. Are there any questions you can directly ask, or I can mediate the questions? Any questions, anyone?
So I can actually answer Özgür's question. So you see, these are people like to use low dimensional stuff because they have more control over this thing. So that's the wire network. But you can actually have, let's say, stuff like basically vortices. They will be also locked to the vortices. You can actually move, if you can move them around. But moving vortices around is not as easy as like basically putting some gates to basically push these excitations around. So that's why people like this idea of this nanowires and things like that. Now people talk about those hinge states and so on. So they want to use that for these type of things and so on. So I mean, so once this door is open, basically you have a lot of topological stuff coming in. You need an isolated low dimensional state, and then you want to be able to proximatize that state with superconductivity. So that's basically the key thing, technologically. I haven't talked about that. Yes, I think I can upload the lecture notes. I think we have a drive. I think I don't know where it is, but I can put it on that drive.
Okay.
So everything was crystal clear. Thank you so much.
So if you have any questions later, maybe you can also email İnanç Hoca.
Oh yeah, I think maybe I should write my email, right? So
yeah, maybe that.
Let me write my email here. It's not really working. I'm just hold on. So let me just write here, so it's on the notes that everybody can reach if they're looking at the notes as well. Email.
Sorry, I missed İnanç's answer, but as far as I understand, it gives you more control at low dimensions, right? In a nutshell.
It gives you more control, and the key thing is that gives you control. If you have because you can actually put gates on it. You can control with gates, and people have, of course, because of semiconductor industry, people feel comfortable with gates. Right, moving vortices around is not easy, and there are actually things like that because you have this Josephson vortices as well, not our old good old abricose vortices that are laying around. But you can also have this thing so-called Josephson vortices, and that happens in this Josephson junction. Those actually, you can also use them to do stuff. But, you know, that's all, you know, there's lots of actually amazing stuff is happening here. Like people have this Josephson junction networks on top of the, you know, this topological insulators, and then doing these things by trying to move vortices, and all sort of crazy stuff. All right, that's it. Let me just
Thank you.
stop the share.